Hello world, welcome to NetModern Tech Academy. Welcome to yet another episode of Python programming. Today we're going to continue from where we left off in the previous video where we did the Connect4 game, and we are going to try and introduce some artificial intelligence into it to make it an interactive game like a player versus a computer. And we are going to use the min-max algorithm for this. The min-max algorithm is very interesting algorithm. You can look it up in YouTube. There are many videos explaining how the algorithm works. But in this video, we're going to focus on implementing this for our Connect4 game that we did in the last video. If you have not checked out the last video, please look in the description. So this was the source code from the last video. Let's start by forking this one. So we'll work from there, make a copy of it. And this is the plain Connect4 game that we played in the console before we did the Pygame for it. And I also noticed a few bugs that I want to fix in this video. Okay, let's get started. So first thing is we want to write some helper methods, more helper methods. I want to know if the game is done, like if there are empty slots to play or if the board is already empty. So I'm going to write a method called count empty slots. And what we are going to do is we are going to pass the self and the board here. So what we are going to do here is we are going to make the count is 0, and then we are going to loop into it for r in range self dot row, or total number of row, and then for c in range self dot call. And whatever board was passed, we are gonna pick up that row. We only have to loop into the rows. We don't need the columns because we can use the count function dot count for the value 0. So our count is going to be plus equal to, and if count is okay, we'll just return the count. So that'll tell us how many empty slots are there still here. So that's good. Now we're gonna make a few changes to the make move method and the check when method. The main change being, instead of always using the self.board, we are going to pass the board as an argument and use that board. I'll explain why we have to do it. Because when we do the min-max algorithm, we are gonna make a copy of the board to look ahead, make the moves and look ahead to see if you are winning or not. Only then we will be able to calculate if it is a better move for the computer or not. So that's why we are passing the board itself. And we're going to do the same for the check win method as well. So what we're going to do in the check win method is we are again going to pass the board here, and we are going to use the board and not simply the self.board. So let's go ahead and make the changes. Perfect. And after doing all these changes, I also noticed one more bug where the negative index kicked in and a wrong win was being calculated. So let's add one more condition here, that when we go back and calculate column minus C, we don't want to go below 0. We don't want -1, -2. That will give us wrong wins. And we need to do the same here as well. So end call minus C is greater than or equal to 0. And for the forward/diagonal. This should actually be calc as C because the columns are increasing here, so as the rows. So row plus C and col plus C. These were a few bugs that I noticed and we are fixing them now. That's good. And now we are going to write one more method to check the win properly. I'll tell you what I mean. So here, check win. I'm just going to call it check win 2, self on the board. What we are going to do here is we are not going to depend on the last move, but we are going to check the complete board to see if somebody has won. So we are going to start a loop for r in range self dot row, and then for c in range self dot column, we are going to assume we are going to first make sure in the board that particular cell is not equal to 0, meaning it's not empty, and we are going to call our check win method. So self dot check win for this particular row and column for the board. And if we notice in our check win method, we always pass the player. So here the player is actually going to be whatever is there in that particular column. So board R, board C. So basically what we are doing is we are checking the winner for every cell and we are going to accept the answer. And if by any chance the answer was something other than -1, that means either player X or player O as 1, then we just return the answer. This way we would have checked the whole board, and if we reach this part of the code, meaning we have completed the whole loop, then we are going to return -1 saying nobody has won. This way we will be able to check all the conditions that we wrote here for all the non-zero elements in the board. Perfect. So that is our check win method. And now to do our min-max algorithm, there should be one more helper function that we need, and we are going to call it get possible moves. So this is going to tell us all the possible moves that we can make in the current state of the board. So how do we get it? If we have at least a 0, an empty slot in that particular column, then it will be a possible move. So let's loop through all the rows, all the columns, and let's see if the top row, the 0th row of that particular column is empty. That means the move can be made in that column. So, and then we are gonna return the moves. So what we are doing is we are checking the topmost row of our board, and if that is 0, that means you can drop a coin in that column. Perfect. And if we look at the min-max algorithm, there is one part here where we have to return a score, which is referred to as heuristic value here. So at any point, we want to be able to score the board. So how does this score work? So according to min-max algorithm, there are two players and one player is trying to minimize the score and the other player is trying to maximize the score, and that's how they both fight for a win. So we are gonna fix the max player, or the player who wants to maximize the score, as X. So when we score the board, what we are going to do is we are going to decide based on who the maximizing player is. So what we are going to do is we are going to find out who is the winner of the board, if anybody is actually winning at this point. So let's find out what is the output when we call the win check win 2 method for the board. If output is actually equal to self.max player, the maximizing player is winning, then we are gonna return let's say 10 points for the maximizing player. L if the output is actually -1, meaning nobody has won, or the game is still on, then we are gonna return 0. After these two options, the only other option is the minimize player is winning or player O. So we are gonna return -10. So if somebody is winning, which is the maximize player, then the score is +10, otherwise 0, otherwise -10. And just to differentiate, if you're winning it early, that is better. So we are also gonna calculate how many empty spots are there in the board. So self dot count empty spots for the board. So 10 plus how many empty spots? So winning at an early stage will give you more score. And the same is true for the minimizing player as well. Winning minus empty spots. So you win with more empty spots in the board, that is better. Perfect. So that is our scoreboard method. Hopefully you were able to follow everything till now. And now we have come to the point where we can actually write a min-max algorithm. So let's get started. We're gonna call it min-max, and we need the self and the board. So what we are gonna do here is we are gonna need a couple of variables here. Node being the board and the depth. Depth meaning how far do you want to simulate the moves? Do you want to simulate till fourth move, third move, how deep you want to go inside the node? So we need the depth, and we also want to know what is the move so we can return the move as the best move for the computer or the AI player to play. And we also want to know who is the current player, for whom are we doing this. So let's get started. According to the algorithm, we are first going to check if the depth is 0 or the node is a terminal node. So let's get started with that. If depth is 0, meaning we have reached the end of our analysis, or if self dot count empty slots for the current board we are at is 0, meaning there are no more slots to play, then it is probably a tie. Or if somebody has won the board, so self dot check win 2 for the board is not equal to -1, meaning somebody has won the game. If any of these things occur, then we have reached the terminal node. So what do? We just return the value of the score. So we are going to return self dot scoreboard for the board. Perfect. So after that, what we are going to do is we are going to check if the current player is the maximizing player, meaning he wants to keep the score high. before this, what we can also do is we want all the moves, all the possible moves. So we will get all possible moves for the board. And if it is a maximize player, the value we are gonna fix it to minus infinity, the most least value. So let's import math. We now have to try and maximize this value. So we start at negative infinity. And we also want to keep track of what is our best move. So what we are going to do now is for each move in moves, we have already found out what are all the possible moves. So for each move, what we are going to do is we are going to make a copy of the board. Now this is very important. And the copy that we make should be a deep copy. We don't want to actually make the move in the board, but only simulate the move. So what we are going to do is we are going to make a deep copy of our board as is. Now we have a copy of it. And we are going to make the move for the current player, the move that we found here for the current copy board. Perfect. Now we have made the move. So what next? We are going to continue this and call the min-max algorithm as a recursive algorithm to go to the next depth level. So self.min-max, we want to pass the board, which will be the copy board. We want to pass the depth, which will be whatever depth we are at, -1. And the move that we actually made here and the current player. We already made the move for the current player. Now we have to make the move for the next player. So we're going to quickly write another helper function called switch player. And what this is going to do is if the player is X, it's going to return O. Else it's going to return X. So we are going to call self.switch player for the current player. So if we did the move for player X, when we call the min-max algorithm again recursively, we will now make the move for player O. Perfect. Now, while we do this, we also want to know what this min-max algorithm is returning. If you remember, it's always going to return the value. And we also, apart from the value, we also want to return the move that was made. So here we have to catch the answer, whatever is being returned. And out of this answer, the second part is the value. So if the current value that we have, or if the answer of 1, which is the value we got, is greater than the current value that we have, then we want to switch the value. We want to maximize the value, right? And when we do this, we also make note of our best move as move. Right? And we have, if we have exhausted all the moves, then we can simply return our best move and our value. Now, we did all this according to the min-max algorithm. So we started with the value of negative infinity, and for each child, we tried to calculate the maximum value by calling the recursive function and doing depth minus 1. Here they are using false and true to switch the players. We are just doing it with a function, switch player. Now we need to do exactly the same for the minimizing player. So we can switch this to else. We start with the value plus infinity, and for all the moves we are gonna make the moves, and if the value is actually less, then we switch it and we return it. Everything else will be the same. Perfect. So now our min-max algorithm is ready, exactly like how it is here. Now let's put it to test. So according to what is written here, the game is a two-player game and the player gets switched every time here. And we start with the player X and we ask the player to input the value. So what we're going to do here is, if player is X, then we are going to ask the player to make the move or enter the move. Else, we are just going to call the min-max algorithm for the current board. And let's start with the depth 4. And let's go move. We are going to say the start move is 0 and the current player is the player. So here, if you remember what the min-max algorithm returns, the min-max algorithm returns the best move and the value. And we are interested in the best move. So here, what we are going to do is we are going to set the call value to answer of 0, which will be the best move. So then the move will automatically happen here for the current player and the winner will be checked and everything should be fine. So now let's run this and check if everything works. So X is the player. Make move is missing a parameter. I think we added a new parameter to the make move function, which was the board in the end. So let's go ahead and pass the board. Let's run it one more time. Check when is also missing, and we're going to replace this to check when 2 and pass c4 dot board here as well. Go ahead. Takes two positional arguments, player and board. We don't have to pass. Let's see, check when 2. What are the parameters? Self board. So all we have to do is pass the board. Okay, let's run it one more time. So 2 and the AI or the computer has made a move already and has put it in the first column. So let's continue playing. I make a move at 1. I make a move at 3. So the computer has made a move at 4 to block me from winning. So let me continue and make a move at 2. And now the computer is trying to win at column 0. So let's stop it at column 0. And now the computer has made a move at column 0 and it says it has won. So something is wrong with our check win logic. Again here, if you notice, maybe the calculation in the column is not working. So let's see what's wrong here. When we do the column, we keep incrementing the row and keep the column the same. And the row value cannot go above 0. So let's add some print statements here to see if we can figure out what is wrong. Or let's try to make the same move and see if we can figure out the values. So here there is actually no win here. So we do not expect the player to win here. So let's try it one more time. So 2, 3, 2, 3, 2, and player O as 1. Let's see what is the winning condition we have. So in check win 2, we have answer self dot check win for this row, this column, board RC and board. And let's see, the win count is at 4. So we are checking the winner here, check when do, and we are printing the winner here. Let's uncomment this one and let's put an input statement here. And in our check when method, let's exactly see which condition is being declared as a winner. So we will print here and say row left, print row right. This will help us debug the issue. Print row, print column. Print diagonal forward slash and print diagonal reverse slash. Escape character has to be done twice. So let's try this one more time. 2, 3, 2, 3. So it says column and row left. So count becomes 0. Let me quickly fix this issue. So check when method and the check when do method. Let me get rid of them and fix them. Let's try this one more time. 2, 3, 2, 3, 2. And now it seems to be working. Everything is good. So we have to get rid of this print statement and this input statement. Let's stop and run this one more time. So 1, 2, 3. Okay, the computer stopped us. Cycle 4. Now we need to try and stop the computer at column 0. And 1, 2, 3, 2, 3. And the computer has now won by doing a diagonal here. So 1, 2, 3, 4. Okay, so that's it, everybody. So what we have done here is we have implemented the min-max algorithm to make a AI player so we can play the Connect4 game with the computer. In the next video, I'll show you how to make this or how to incorporate this into our Pygame code that we have done already. I'll talk to you all in the next video soon. Until then, take care. Bye, world.